Have you ever pondered about the nature of reality and how it's defined by the quantum world? Welcome to the fascinating realm of quantum physics, where our understanding of the universe gets a little bit quirky. Let's dive into one of its most puzzling concepts, quantum entanglement. This is a phenomenon that defies our everyday understanding of how the world works. Imagine two particles, separated by vast distances, behaving as if they are one and the same. What happens to one instantaneously affects the other, no matter how far apart they are. It's as if these particles are entwined in a cosmic dance choreographed by the laws of quantum mechanics. This concept was so counterintuitive that even Albert Einstein, one of the greatest minds in physics, wrestled with it. He famously referred to it as spooky action at a distance. This brings us to the intriguing and mind-boggling phenomenon of quantum entanglement. But what exactly is quantum entanglement? Imagine a pair of dice. Quantum entanglement is a bit like having two dice that are always perfectly in sync. You roll them, and no matter how far apart they are, they always land on the same number. Now that's easy to imagine because we could rig the dice to always land on, say, a 6. But what if I told you that these dice are not rigged, and each roll is still totally random? Here's where it gets even stranger. Not only do they always land on the same number, but neither die actually chooses its number until the moment you look at it. They're in a state of uncertainty, with all possibilities open until observed. That's the essence of quantum entanglement. It's like having a pair of gloves, where, until you open the box they're in, each glove is both left-handed and right-handed at the same time. As soon as you look at one, it becomes, let's say, a left glove. And that very instant, no matter how far away the other glove is, it becomes a right one. This seems to violate the universal speed limit, the speed of light, because the communication between the two particles is instantaneous. It's as though they're not just sending messages to each other, they're actually the same entity behaving as one no matter the distance between them. Einstein wasn't a fan of this idea. He called it spooky action at a distance, and he thought it revealed that quantum mechanics was incomplete. But experiments have shown over and over that quantum entanglement is real. Particles really do seem to be linked in this weird, instantaneous way. So, despite Einstein's reservations, experiments have confirmed this spooky action at a distance. This doesn't mean that quantum mechanics is complete or that we have all the answers, far from it. But it does mean that the universe might be even stranger than we thought. This leads us into the realm of the Einstein-Podolsky-Rosen paradox and the concept of non-locality. The Einstein-Podolsky-Rosen paradox, commonly known as the EPR paradox, is a thought experiment proposed by Albert Einstein, Boris Podolsky, and Nathan Rosen in 1935. They aimed to demonstrate that the theory of quantum mechanics, as it was then understood, was incomplete. The paradox is based on the principle of locality, which states that an object can only be influenced by its immediate surroundings. However, quantum entanglement seems to violate this principle. When two particles become entangled, the state of one instantly affects the state of the other, no matter the distance separating them. This instant communication, faster than the speed of light, is what Einstein famously referred to as spooky action at a distance. And here's where we encounter the concept of non-locality. Non-locality in quantum mechanics refers to the idea that entangled particles are connected in such a way that their states correlate instantaneously, regardless of the distance between them. This defies our everyday understanding of space and time, suggesting the existence of some deeper layer of reality that we're yet to fully comprehend. In essence, the EPR paradox and non-locality challenge our conventional understanding of the universe. They question the very fabric of our reality, hinting at the existence of a world far more complex and interconnected than we could ever imagine. Einstein, Podolsky, and Rosen hoped their paradox would prove that quantum mechanics was flawed or incomplete. However, their work instead led to the discovery of some of the most mind-bending aspects of quantum physics. It opened up a new world of possibilities, full of quantum entanglement, superposition, and non-locality. So, while the paradox might have initially seemed like a problem for quantum mechanics, it ultimately became one of its greatest strengths. It's these very paradoxes, these very challenges to our understanding that push us to dig deeper, to learn more, to question and explore. So, entanglement might just be the key to unlocking a deeper understanding of the universe. But beyond the philosophical implications, quantum entanglement also holds promising applications in technology. Let's start with quantum computing. Traditional computers use bits as their smallest unit of information, which can either be a 0 or a 1. Quantum computers, however, use quantum bits or qubits that can be both 0 and 1 simultaneously, thanks to a quantum principle known as superposition. Now throw in entanglement, and we have a system where changing the state of one qubit can instantaneously change the state of another, no matter the distance. This could potentially allow quantum computers to solve certain problems much faster than any supercomputer. Next, we have quantum cryptography, a field that leverages the principles of quantum mechanics to secure data transmission. Imagine two entangled particles, each sent to separate recipients. If an eavesdropper tries to intercept the message, the very act of measuring will alter the state of the particles, alerting the recipients to the intrusion. This is the essence of quantum key distribution, a method that could provide uncrackable security for our digital communications. Lastly, let's touch on quantum teleportation. No, it's not about beaming humans across space like in a science fiction movie. Instead, it's about transferring the state of a quantum particle to another distant particle. Two entangled particles can be used to transmit quantum information from one location to another, instantaneously and without a physical medium. This could revolutionize communication technologies and perhaps even give rise to new forms of quantum internet. These are just a few glimpses into the potential of quantum entanglement in technology. Of course, we're still in the early stages of exploring these possibilities, and there are numerous challenges to overcome, but the potential is immense. As we continue to unravel the mysteries of the quantum world, we may find solutions to some of our most complex problems and open doors to possibilities we can't even imagine yet. Indeed, the quantum world, as strange as it may be, could hold the keys to our technological future. To wrap up, quantum entanglement is a fascinating, if somewhat mind-bending, aspect of quantum physics. It's a phenomenon that seems to defy our everyday understanding of reality. The counterintuitive nature of entangled particles communicating instantaneously, regardless of the distance between them, challenges our perception of locality and causality. This mysterious concept has been brilliantly demonstrated through real-world experiments, lending credence to its existence beyond the realm of mere theoretical physics. Moreover, the implications of quantum entanglement to our understanding of reality are profound. It plays a central role in the Einstein-Podolsky-Rosen paradox and the concept of non-locality, further deepening the mystery of the quantum world. But quantum entanglement isn't just about philosophical contemplation. It promises to revolutionize our technological landscape. Potential applications in quantum computing, cryptography, and even teleportation could lead us into a new era of technological advancement. So next time you roll a pair of dice, remember, in the quantum world, things might not be as they seem.